Subscribe to the channel so you don't miss out on any of these videos. Space is vast, mysterious, and filled with wonders that have fascinated humanity for millennia. Our journey into the mysteries of space has only just begun, and even with all the advances in technology and astronomy, we still know so little. Every star, planet, and galaxy holds secrets waiting to be discovered, and the sheer scale of the universe can boggle the human mind. The mysteries of space span everything from the smallest particles to the largest structures in the universe, and they challenge our understanding of physics, life, and even time itself. One of the most perplexing mysteries of space is the nature of dark matter and dark energy. While visible matter, such as planets, stars, and galaxies, make up only about 5% of the universe, the rest consists of these mysterious substances. Dark matter, which makes up about 27% of the universe, doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Its presence was first suggested to explain the way galaxies rotate. Without dark matter, they would tear themselves apart due to the speed at which they spin. But what is dark matter made of? Scientists have proposed various candidates, such as weakly interacting massive particles, WIMPs, and axions, but so far, no direct detection has been made. This invisible substance could hold the key to understanding the very fabric of the cosmos. Dark energy is even more enigmatic. It makes up approximately 68% of the universe and is thought to be responsible for the accelerated expansion of the universe. When the universe was first discovered to be expanding, it was assumed that the rate of expansion would slow down over time due to the gravitational pull of matter. However, observations in the late 20th century revealed that the expansion is actually speeding up. This led to the hypothesis of dark energy, a mysterious force that works in opposition to gravity, pushing galaxies apart. But what exactly is dark energy? Is it a property of space itself, or is it something even more fundamental? Understanding dark energy could revolutionize our understanding of cosmology and provide insights into the ultimate fate of the universe. Another profound mystery is the existence of black holes, regions of space where gravity is so intense that not even light can escape. First predicted by Albert Einstein's theory of general relativity, black holes are formed when massive stars collapse under their own gravity at the end of their life cycles. These cosmic objects have been observed indirectly through the behavior of nearby stars and gas, which are drawn into the black hole's gravitational pull. But what's inside a black hole? At the center lies a singularity, a point where the laws of physics as we know them break down, and densities become infinite. The event horizon, the boundary around the black hole, marks the point of no return. Anything that crosses it is doomed to be pulled into the singularity. But what happens to the matter that falls into a black hole? Does it get destroyed, or does it travel to another part of the universe or even another universe entirely? One of the most intriguing aspects of black holes is their potential to connect to other regions of space and time. Theoretical physicists have proposed the idea of wormholes, which are hypothetical tunnels through spacetime that could link distant parts of the universe. If wormholes exist, they could provide a shortcut for space travel, allowing faster-than-light journeys. However, the stability of wormholes is highly uncertain, and they may collapse before anything can pass through them. Moreover, the intense gravitational forces near a black hole would likely tear apart any object attempting to enter a wormhole. While these ideas remain speculative, they challenge our understanding of space and time and raise questions about the very nature of reality. Beyond black holes and dark matter, space is filled with other cosmic mysteries. One of the most enduring questions is whether we are alone in the universe. With billions of stars in our galaxy alone and trillions more in the observable universe, it seems statistically likely that life exists elsewhere. Yet, despite decades of searching, we have found no conclusive evidence of extraterrestrial life. The Fermi paradox, named after physicist Enrico Fermi, asks, if intelligent extraterrestrial civilizations exist, why haven't we detected any signs of them? There are many possible answers to this question. Perhaps intelligent life is extremely rare, or maybe civilizations inevitably destroy themselves before they can develop advanced spacefaring technologies. It's also possible that extraterrestrial civilizations are out there but are choosing not to communicate with us or are using technologies we don't yet understand. The search for extraterrestrial life isn't just limited to distant star systems. In our own solar system, there are several places that could potentially harbor life. Europa, one of Jupiter's moons, has a subsurface ocean beneath its icy crust, and scientists believe that this ocean could provide the conditions necessary for life. Similarly, Saturn's moon Enceladus has water ice geysers that spew material from a subsurface ocean into space, hinting at the possibility of microbial life beneath its surface. Even Mars, with its barren landscape, has evidence of ancient river valleys and lakebeds, suggesting that it may have once had liquid water on its surface. While no definitive evidence of life has been found on any of these worlds, the discovery of even microbial life elsewhere in the solar system would have profound implications for our understanding of biology and the potential for life throughout the universe. The study of exoplanets, planets orbiting stars outside our solar system, has also opened new possibilities in the search for life. Since the discovery of the first exoplanet in 1992, thousands of these distant worlds have been identified, and many are located in the habitable zone of their parent stars, where conditions might be right for liquid water to exist. Some exoplanets are even similar in size and composition to Earth, raising the tantalizing possibility that they could support life. However, detecting life on exoplanets is extremely challenging, and current technology is only beginning to scratch the surface of what might be possible in the future. In addition to the search for life, space also presents mysteries about the nature of time itself. Einstein's theory of relativity showed that time is not a fixed, universal constant but is relative, depending on the observer's motion and the gravitational field they are in. This leads to the phenomenon known as time dilation, where time moves more slowly in stronger gravitational fields or for objects moving at high speeds. Near a black hole, for example, time would pass much more slowly for an observer compared to someone far away from the black hole. This raises fascinating possibilities for space travel. Could we, in theory, travel to distant stars and return to Earth to find that thousands of years have passed while only a short time has elapsed for us? The concept of time travel, long a staple of science fiction, is also taken seriously by some physicists. While traveling into the future is theoretically possible according to Einstein's theory, traveling into the past is far more complicated and may involve paradoxes. One proposed solution to these paradoxes is the idea of parallel universes, where changes in the past create new branches of reality. This leads to the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of a quantum event creates a new, parallel universe. If this interpretation is correct, there could be an infinite number of parallel universes, each with its own version of reality. Parallel universes raise even more questions about the nature of space and time. Could there be other versions of ourselves living in alternate realities, making different choices and experiencing different outcomes? Some theories suggest that black holes could be gateways to other universes, or that the Big Bang, which gave birth to our universe, was just one of many such events, with each creating its own separate universe. If true, this would mean that the universe we live in is just one small part of a much larger multiverse, a concept that challenges our understanding of existence itself. The idea of a multiverse is one of the most mind-bending concepts in modern cosmology. While it may sound like science fiction, there are serious scientific theories that suggest the existence of multiple universes. One such theory comes from the realm of quantum mechanics, which governs the behavior of particles on the smallest scales. In the quantum world, particles don't behave in a deterministic way, but rather, they exist in a state of probability until observed. This led to the many worlds interpretation, where every possible outcome of a quantum event actually happens, but in different, parallel universes. So, if you flip a coin, in one universe it lands heads, and in another universe it lands tails. If this interpretation is correct, it implies that there are an infinite number of universes, each one representing a different version of reality. Another version of the multiverse theory comes from string theory, which attempts to reconcile quantum mechanics with general relativity. String theory suggests that all particles are actually tiny, vibrating strings, and these strings exist in higher dimensions beyond the familiar 3 dimensions of space and 1 of time. In some versions of string theory, our universe is just one of many brains floating in a higher dimensional space. These brains could collide, creating new universes in the process, which might explain the Big Bang. This multiverse of brains could contain an infinite number of universes, each with its own laws of physics, some of which might be completely different from our own. One of the most puzzling aspects of our universe is that it appears to be finely tuned for life. The fundamental constants of nature, such as the strength of gravity and the electromagnetic force, seem to be set at just the right values to allow the existence of atoms, stars, planets, and ultimately, life. If any of these constants were even slightly different, life as we know it would not be possible. This has led some to propose the anthropic principle, which suggests that we live in a universe that is capable of supporting life simply because, if it weren't, we wouldn't be here to observe it. In other words, the universe must be suitable for life because we are here to notice it. However, the multiverse theory offers another explanation. If there are an infinite number of universes, each with different physical constants, then it's not surprising that at least one universe, ours, has the right conditions for life. The mysteries of the universe don't stop with the large-scale structure of space and time. They also extend to the very fabric of reality at the smallest scales. Quantum mechanics, the branch of physics that describes the behavior of particles at the atomic and subatomic levels, is full of paradoxes and strange phenomena. One of the most famous of these is the concept of quantum entanglement, where 2 particles can become linked in such a way that the state of one particle instantly affects the state of the other, even if they are separated by vast distances. This phenomenon, which Albert Einstein famously called spooky action at a distance, has been experimentally confirmed, yet it defies our intuitive understanding of how the universe works. How can 2 particles communicate instantaneously, seemingly faster than the speed of light? This mystery challenges our very notions of space and causality. Quantum mechanics also gives rise to the famous Schrödinger's cat thought experiment, where a cat is placed in a box with a quantum device that has a 50-50 chance of killing the cat. According to quantum mechanics, until the box is opened and the cat is observed, it exists in a superposition of states, both alive and dead. This paradox highlights the strange and counterintuitive nature of quantum reality, where particles can exist in multiple states at once until they are measured. But what does this mean for our understanding of reality? Does consciousness play a role in collapsing the wave function and determining the outcome of quantum events? These questions remain unanswered and lie at the heart of some of the deepest mysteries of space and physics. Another mystery that has puzzled scientists for decades is the origin and fate of the universe. The prevailing theory for the origin of the universe is the Big Bang, which suggests that the universe began as an incredibly hot, dense point about 13.8 billion years ago, and has been expanding ever since. This theory is supported by several lines of evidence, including the cosmic microwave background radiation, which is the afterglow of the Big Bang, and the observation that galaxies are moving away from each other, indicating that the universe is expanding. But what caused the Big Bang? Was it a random event, or was there something before the Big Bang that set the stage for the creation of the universe? Some theories suggest that the Big Bang was not the beginning of time but rather a transition from a previous phase of the universe. For example, the Big Bounce theory proposes that the universe goes through cycles of expansion and contraction, with the Big Bang marking the transition from one cycle to the next. The ultimate fate of the universe is also a subject of intense speculation. If the universe continues to expand indefinitely, it could lead to a big freeze, where galaxies move so far apart that stars burn out, and the universe becomes a cold, dark, and empty place. Alternatively, if the expansion of the universe slows down and reverses, it could lead to a big crunch, where the universe collapses back in on itself, possibly leading to another Big Bang and the birth of a new universe. Yet another possibility is the Big Rip, where the expansion of the universe accelerates to the point that it tears apart galaxies, stars, planets, and even atoms. The fate of the universe is tied to the nature of dark energy, which remains one of the greatest mysteries in cosmology. In addition to these large-scale mysteries, space also holds many unanswered questions about the nature of stars, planets, and other celestial objects. For example, astronomers have discovered exoplanets, planets orbiting stars outside our solar system, in a wide variety of sizes and types, from gas giants larger than Jupiter to rocky planets smaller than Earth. Some exoplanets are located in the habitable zone of their stars, where conditions might be right for liquid water to exist, raising the possibility of life. But how common are Earth-like planets, and how often do they develop life? While we have identified thousands of exoplanets, we still know very little about their atmospheres, climates, and potential habitability. Future telescopes, such as the James Webb Space Telescope, may provide more detailed observations that could help answer these questions. Another mystery involves the process of star formation. Stars are born from vast clouds of gas and dust that collapse under their own gravity, but the details of this process are still not fully understood. What triggers the collapse of a gas cloud to form a star, and how do stars of different sizes and types form? Massive stars, for example, have much shorter lifespans than smaller stars like our Sun, and they end their lives in spectacular supernova explosions. These explosions can create black holes or neutron stars, and they play a crucial role in dispersing heavy elements, such as carbon and oxygen, into space, which are necessary for the formation of planets and life. But the exact mechanisms behind these processes remain a topic of ongoing research. Supernovae themselves are among the most powerful and mysterious events in the universe. These stellar explosions can outshine entire galaxies for a short period of time, and they release immense amounts of energy and matter into space. But not all supernovae are the same, and some types are still poorly understood. For example, Type I supernovae occur in binary star systems, where a white dwarf star accretes matter from its companion until it reaches a critical mass and explodes. These supernovae are used as standard candles to measure distances in the universe because they have a consistent brightness. However, recent observations have shown that not all Type I supernovae behave as expected, raising questions about their use in cosmology. In addition to the mysteries surrounding supernovae, the life cycles of stars hold many secrets that are yet to be fully uncovered. Stars like our Sun will eventually burn through their fuel and transition into a red giant before shedding their outer layers and leaving behind a dense core known as a white dwarf. However, for more massive stars, the end of life can be far more dramatic, often resulting in the formation of a neutron star or a black hole, depending on the star's initial mass. Neutron stars, which are made almost entirely of neutrons, are incredibly dense, with a mass comparable to that of the Sun but compressed into a sphere only about 10 kilometers in diameter. This creates some of the most extreme conditions in the universe, where matter is packed so tightly that a sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. One of the most fascinating phenomena associated with neutron stars is the existence of pulsars. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As these beams sweep across the Earth, they create a pulsating effect, which is how pulsars got their name. The discovery of pulsars in the 1960s was a major breakthrough in astrophysics, and they remain an area of active research. The precise mechanism that generates the powerful beams of radiation from pulsars is still not fully understood, and studying these enigmatic objects could provide valuable insights into the behavior of matter under extreme conditions. Even more mysterious than neutron stars are magnetars, a type of neutron star with an extraordinarily strong magnetic field, up to 1,000 times stronger than that of a typical neutron star. The magnetic fields of magnetars are so intense that they can cause the star's crust to crack, releasing bursts of X-rays and gamma rays in the process. These starquakes are some of the most energetic events in the universe, and they challenge our understanding of how magnetic fields interact with matter. Magnetars are thought to be relatively rare, but their extreme nature makes them a crucial piece of the puzzle when it comes to understanding the most exotic objects in the cosmos. One of the more speculative mysteries of space concerns the potential existence of quark stars. These hypothetical objects would be even denser than neutron stars, made not just of neutrons but of their constituent particles, quarks. Quarks are the building blocks of protons and neutrons, and under the right conditions, it's possible that a neutron star could collapse into an even more compact state of quark matter. If quark stars exist, they would be among the strangest objects in the universe, with properties that defy current models of astrophysics. However, no direct evidence for quark stars has been found, and their existence remains a theoretical possibility. Another cosmic mystery that continues to perplex scientists is the nature of fast radio bursts, FRBs. These are extremely powerful, but brief, bursts of radio waves that originate from distant galaxies. The first FRB was discovered in 2007, and since then, hundreds more have been detected, yet their origin remains a mystery. Some FRBs repeat, while others seem to be one-off events, and their sources could range from exotic objects like magnet stars to more speculative explanations, including advanced alien civilizations. The energy released by an FRB in just a few milliseconds can be equivalent to the total energy output of the Sun over several days, highlighting just how extreme these events are. Although researchers have made progress in pinpointing the locations of some FRBs, much remains unknown about what causes them and why they occur with such variety. Moving away from stars and exotic objects, the structure of the universe itself presents some of the most profound mysteries. Galaxies are not distributed randomly throughout the universe but are instead arranged in vast, interconnected webs of cosmic filaments and voids. These large-scale structures, known as the cosmic web, are shaped by the gravitational influence of dark matter and have been mapped in increasingly greater detail through surveys of the sky. Yet, questions remain about how this intricate structure formed and evolved over time. One particularly striking feature of the universe is the existence of supervoids, enormous regions of space that contain far fewer galaxies than average. These voids can span hundreds of millions of light-years across, and their emptiness poses questions about how galaxies and matter became so concentrated in certain regions while leaving others so barren. On the flip side, we also have superclusters of galaxies, massive structures that contain thousands of galaxies and are bound together by gravity. Understanding how such large structures formed in the early universe and how they relate to the distribution of dark matter is a key challenge in cosmology. Another fascinating enigma is the discovery of ultra-diffuse galaxies. These ghostly galaxies are as large as the Milky Way but contain very few stars, making them nearly invisible against the blackness of space. Some ultra-diffuse galaxies appear to be devoid of dark matter, which is unusual because dark matter is thought to play a crucial role in the formation and stability of galaxies. How these faint, dark matter-deficient galaxies formed, and how they have survived without being disrupted by gravitational forces, remains a puzzle. Their existence could challenge current models of galaxy formation and evolution, forcing scientists to reconsider how galaxies come into being and interact with their surroundings. When it comes to the mysteries of space, one of the most awe-inspiring phenomena is the cosmic microwave background, CMB, radiation. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of the universe when it was just 380,000 years old. The discovery of the CMB in 1965 was a major milestone in cosmology, as it confirmed the Big Bang theory and gave us a glimpse of the universe's earliest moments. However, the CMB also presents puzzles. Tiny fluctuations in the CMB's temperature and density provide clues about the early distribution of matter and energy in the universe, but there are anomalies in the data that don't fit neatly with our current understanding of cosmology. For example, the cold spot in the CMB is an unusually large region of space that is cooler than expected, and some scientists have speculated that it could be the imprint of a collision with another universe in the multiverse. Additionally, the CMB shows that the universe is remarkably uniform on large scales, yet structures like galaxies and clusters of galaxies have formed. This leads to questions about how small fluctuations in the early universe grew into the large-scale structures we see today. The process of cosmic inflation, a rapid expansion of the universe in its earliest moments, is thought to explain this uniformity, but inflation itself remains poorly understood. What caused inflation, and why did it stop? These questions are central to understanding the origins of the universe and how it evolved into its current state. As we delve deeper into the mysteries of space, we are constantly reminded of how much we still don't know. One of the biggest open questions in cosmology is the true nature of the universe's expansion. Observations of distant galaxies show that the universe is expanding at an accelerating rate, driven by the mysterious force known as dark energy. But how does dark energy work? Is it constant, or does it change over time? Some theories suggest that dark energy could eventually reverse its effect, leading to a big crunch, where the universe collapses back in on itself. Others propose that dark energy could grow stronger, leading to a big rip, where the universe's expansion tears apart galaxies, stars, and even atoms. Alternatively, the universe could continue expanding forever, gradually cooling and fading into a state of heat death, where all matter is evenly distributed and no further processes can occur. This uncertain fate of the universe is tied to another mystery: the true shape of the universe. Is the universe flat, open, or closed? A flat universe would expand forever, while a closed universe could eventually collapse. Current observations suggest that the universe is very close to being flat, but small deviations could exist that we haven't yet detected. Determining the precise shape of the universe could help answer questions about its ultimate fate and the role of dark energy in driving its expansion. As we explore the fate of the universe, we inevitably encounter the question of whether the universe had a beginning and if it might have an end. The prevailing theory of the Big Bang suggests that the universe began around 13.8 billion years ago from an incredibly hot, dense state, expanding ever since. However, what caused the Big Bang? What existed before it, if anything at all? These questions push the boundaries of our understanding of time and space. Some theories propose that the Big Bang was not a singular event, but rather one of many cycles in which the universe expands and contracts over and over again in a process called the Big Bounce. In this scenario, the universe could be eternal, with no definitive beginning or end. Another hypothesis is that the Big Bang was triggered by the collision of two higher-dimensional branes, vast surfaces existing in a higher-dimensional space. This idea, part of string theory, suggests that our universe could be just one of many in a vast multiverse, each with its own unique properties. The idea of the multiverse opens up even more questions. If multiple universes exist, how many are there? Are they parallel to our own, with slight variations in physical laws and constants? Or are they completely different, with unknown rules and structures? The concept of the multiverse challenges our understanding of reality itself, as it implies that the universe we inhabit is just one tiny corner of a much larger and more complex cosmic landscape. While there is no direct evidence for the multiverse, it remains a tantalizing possibility that could one day revolutionize our understanding of space and existence. Another area of space that captures the imagination is the idea of wormholes. These theoretical shortcuts through space-time could, in principle, allow for faster-than-light travel between distant parts of the universe. A wormhole connects 2 points in space through a tunnel-like structure, bypassing the vast distances that separate them. Although wormholes have been predicted by the equations of general relativity, they remain purely speculative, as no wormholes have been observed, and it is unclear whether they could actually exist in a stable form. If they do exist, wormholes could open up incredible possibilities for space travel, allowing us to explore distant galaxies in a fraction of the time it would take using conventional methods. Wormholes also raise the intriguing possibility of time travel. In theory, if one end of a wormhole were accelerated to near the speed of light or placed in a strong gravitational field, time could pass differently at each end, creating a time machine. However, time travel introduces paradoxes, such as the famous grandfather paradox, where a time traveler could potentially prevent their own existence by altering events in the past. These paradoxes suggest that time travel may be impossible, or that the universe has mechanisms in place to prevent such contradictions. Nevertheless, the possibility of time travel remains one of the most fascinating and perplexing mysteries in both science and fiction. Time itself is one of the great mysteries of space. While we experience time as a continuous flow, physicists view it as a dimension, much like space. In the theory of relativity, time and space are intertwined in a four-dimensional fabric known as spacetime. The passage of time can be affected by gravity and motion, an effect known as time dilation. For example, a clock near a massive object like a black hole will tick more slowly than one far away from such an object. Similarly, a clock on a spaceship traveling at near the speed of light would run slower than one on Earth. These effects, while subtle in everyday life, have profound implications for our understanding of time and reality. The concept of time becomes even more complex when we consider the possibility that time might not flow in only one direction. The second law of thermodynamics states that the entropy, or disorder, of a closed system tends to increase over time, giving rise to the arrow of time, the idea that time moves from the past to the future. However, in the equations of physics, time is symmetrical, meaning that processes can theoretically occur in either direction. This raises the question of why we experience time as moving forward. Some physicists suggest that the arrow of time is a consequence of the universe's initial conditions following the Big Bang, while others propose that time may behave differently in different parts of the multiverse. Dark matter and dark energy further complicate our understanding of space and time. Together, these two mysterious components make up about 95% of the universe's total mass energy content, yet we have no direct knowledge of their nature. Dark matter interacts with regular matter through gravity but does not emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred from its gravitational effects on galaxies and galaxy clusters, where it appears to act as an invisible scaffolding, holding these structures together. Various candidates have been proposed for dark matter, including weakly interacting massive particles, WIMPs, sterile neutrinos, and axions. However, despite extensive efforts to detect dark matter particles directly, no conclusive evidence has been found. Understanding dark matter is one of the key challenges in modern physics, as it could unlock new insights into the fundamental workings of the universe. Dark energy, on the other hand, is even more mysterious. It is the name given to the unknown force driving the accelerated expansion of the universe, and it seems to counteract the effects of gravity on cosmic scales. One possibility is that dark energy is a property of space itself, an intrinsic energy that becomes more dominant as the universe expands. Another possibility is that our understanding of gravity may be incomplete, and that the accelerated expansion could be a sign that we need a new theory of gravity. Either way, solving the mystery of dark energy will require a deeper understanding of the fundamental forces that govern the universe. As we look beyond the visible universe, we are confronted with another perplexing question: what lies beyond the observable universe? The observable universe is limited by the speed of light and the finite age of the universe. Because light from more distant regions has not had time to reach us, we can only observe a portion of the entire universe. However, the universe is likely much larger than what we can see, and it could even be infinite. If the universe is infinite, it raises the possibility that regions beyond the observable universe could be vastly different from what we know, with different physical laws, constants, and even entirely different types of matter. The idea that the universe could be infinite leads to further speculation about its origins and structure. If space goes on forever, does that mean that every possible configuration of matter eventually repeats itself? Could there be an infinite number of identical Earths, each with its own version of you reading this essay? This is one of the more mind-bending implications of an infinite universe, and while it remains speculative, it illustrates just how much we still have to learn about the cosmos. Even within the observable universe, we face the mystery of the distribution of matter. While galaxies and galaxy clusters are scattered throughout space, there are regions known as voids that contain very little matter. These cosmic voids are vast expanses of nearly empty space, sometimes hundreds of millions of light-years across. How did these voids form, and what can they tell us about the evolution of the universe? Understanding the large-scale structure of the universe, including the distribution of galaxies, voids, and cosmic filaments, is crucial for unraveling the mysteries of dark matter, dark energy, and cosmic expansion. One of the most intriguing questions about space is whether life exists elsewhere in the universe. The sheer number of stars and planets in the universe suggests that the conditions for life could be common, Yet we have not detected any signs of extraterrestrial civilizations. This paradox is known as the Fermi paradox. If the universe is so vast and old, and if life is relatively common, why haven't we found any evidence of it? Various explanations have been proposed, ranging from the possibility that intelligent life is extremely rare or short-lived, to the idea that advanced civilizations are deliberately avoiding contact with us. One possibility to explain the Fermi paradox is that intelligent civilizations may not use detectable forms of communication, or that their technology is so advanced that we cannot recognize it. Another hypothesis is that civilizations may destroy themselves before they reach the stage of interstellar communication, possibly due to wars, environmental collapse, or other self-inflicted disasters. This idea raises questions about the future of humanity, and whether we will manage to avoid such a fate as we continue to advance technologically. Other theories suggest that we may be looking in the wrong places or using the wrong methods to search for extraterrestrial life. The search for extraterrestrial intelligence, SETI, has focused largely on detecting radio signals from other civilizations, but it's possible that more advanced forms of communication exist that we are not yet capable of understanding or detecting. Additionally, extraterrestrial life might not resemble life as we know it. Life forms on other planets could be based on different biochemistries, such as silicon rather than carbon, or they could exist in environments that are inhospitable to us, such as the atmospheres of gas giants, or the icy oceans of moons like Europa and Enceladus. Another fascinating possibility is that life exists in the form of self-replicating artificial intelligence or machines, which may have little interest in communicating with biological life forms like us. Such entities could have spread throughout the galaxy, quietly observing or harvesting resources without leaving obvious traces of their presence. This concept, known as the machine hypothesis, challenges our assumptions about what intelligent life might look like and how it might behave. The search for life beyond Earth is not limited to intelligent civilizations. Astrobiologists are also focused on the potential for microbial life in our own solar system. Moons such as Europa, Enceladus, and Titan have oceans beneath their icy crusts, which may harbor conditions suitable for life. The discovery of microbial life elsewhere in the solar system would be profound, as it would suggest that life can arise in a wide variety of environments, increasing the likelihood that it is common throughout the universe. The study of exoplanets, planets that orbit stars outside our solar system, has also opened up new possibilities for finding habitable worlds. Thousands of exoplanets have been discovered in recent years, many of which reside in the so-called habitable zone of their stars, where conditions might allow for liquid water to exist. However, being in the habitable zone does not guarantee that a planet is capable of supporting life, as many other factors, such as atmospheric composition and magnetic fields, play a role in making a planet hospitable. The discovery of Earth-like exoplanets raises the tantalizing possibility that life may exist on planets similar to our own. Future space telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, may be able to analyze the atmospheres of these distant worlds, searching for signs of life such as oxygen, methane, or other biomarkers. However, even if we find strong evidence for life on an exoplanet, it may take decades or even centuries before we can send a spacecraft to confirm its existence, given the vast distances involved. The possibility of life on other planets also brings up the question of how life originated in the first place. The origin of life, or abiogenesis, is one of the greatest mysteries in biology and cosmology. Scientists have proposed various theories about how life could have arisen from non-living matter, but the exact process remains unknown. One possibility is that life began in deep-sea hydrothermal vents, where the combination of heat, minerals, and chemicals created the conditions necessary for the first simple organisms to form. Another idea is that life may have originated on land, in small, warm ponds or near volcanic hot springs. A more controversial theory is known as panspermia, which suggests that life on Earth may have originated elsewhere in the universe and was brought here by comets, asteroids, or other celestial bodies. If true, this would mean that life could have spread throughout the galaxy, potentially seeding multiple planets with the ingredients for life. While panspermia does not explain how life began, it raises intriguing possibilities about the interconnectedness of life in the universe and the potential for common origins across distant worlds. As we explore the mysteries of life in the universe, we are also confronted with fundamental questions about the nature of consciousness. Human consciousness is one of the most complex and enigmatic phenomena we know, and it remains poorly understood by both scientists and philosophers. Is consciousness a product of the brain, or is it something more fundamental, perhaps linked to the fabric of the universe itself? Some theories suggest that consciousness may be a basic property of the universe, much like space and time, and that it could exist in different forms throughout the cosmos. If consciousness is not unique to humans, it raises the question of whether other forms of life, including extraterrestrial beings, could also possess conscious awareness. What would alien consciousness look like, and how might it differ from our own? These questions challenge our understanding of intelligence and awareness, and they hint at the possibility that the universe is more alive and conscious than we currently realize. The idea of a conscious universe brings us to another profound mystery: the role of humans in the cosmos. Are we simply insignificant beings living on a small planet in a vast, indifferent universe, or do we have a special role to play in the grand scheme of things? Some thinkers have proposed that human consciousness and creativity may be central to the universe's evolution, suggesting that the universe is designed in such a way that it produces beings capable of observing and understanding it. This concept, known as the anthropic principle, has been interpreted in various ways, from a simple statement about the conditions necessary for life to more speculative ideas about the purpose of existence. On the other hand, the vastness and apparent indifference of the universe can also lead to existential questions about the meaning of life. If the universe is so large and so old, with billions of galaxies and potentially trillions of planets, what is the significance of human life in the grand cosmic picture? Philosophers and theologians have grappled with these questions for centuries, and while science can provide insights into the physical workings of the universe, it may never be able to fully answer the deeper questions of purpose and meaning. The mysteries of space also challenge our understanding of time and eternity. The universe, as far as we know, is finite in both time and space. It had a beginning with the Big Bang, and it may have an end, whether through heat death, a big crunch, or some other process. However, the idea of an eternal universe, or an eternal multiverse, raises questions about the nature of time itself. Can time truly go on forever, or is it bound to come to an end? And if the universe does end, what, if anything, lies beyond that? One possibility is that time is cyclical, with the universe undergoing endless cycles of creation and destruction. This idea is found in some ancient philosophies and has been explored in modern cosmological theories, such as the Big Bounce. In this view, the universe might be eternal, but its individual cycles of expansion and contraction are finite. Alternatively, the universe could experience a quantum rebirth after its end, with new universes constantly being born from the remnants of old ones. Quantum mechanics, which governs the behavior of particles on the smallest scales, also introduces strange possibilities for the nature of reality. According to the principles of quantum mechanics, particles can exist in multiple states at once until they are observed, a phenomenon known as superposition. This has led to the idea that the universe itself could exist in multiple states or even multiple realities, depending on how it is observed. The famous thought experiment of Schrödinger's cat illustrates this paradox, where a cat in a box can be both alive and dead until someone opens the box and observes it. These strange implications of quantum mechanics have given rise to various interpretations, including the many worlds interpretation, which suggests that every possible outcome of a quantum event actually occurs, but in separate, branching universes. If this interpretation is correct, it would mean that there are countless parallel universes, each with its own version of reality. This idea connects back to the concept of the multiverse and suggests that our universe may just be one of many coexisting realities. The mysteries of space are not confined to the physical universe alone. They also touch on the deepest questions of existence, consciousness, and the nature of reality itself. From the origins of the universe to the possibility of life beyond Earth, From the enigma of dark matter and dark energy to the profound implications of quantum mechanics, space continues to challenge and expand our understanding of the cosmos and our place within it. As we continue to explore space, both through scientific observation and through the lens of imagination, we are likely to uncover even more mysteries and paradoxes that will push the boundaries of human knowledge. The journey to understand the universe is a never-ending quest, one that will likely continue for generations to come. And in that quest, we may not only learn more about the cosmos, but also about ourselves and the nature of existence. In exploring the vast mysteries of space, one of the most tantalizing subjects is the potential for faster-than-light travel. Currently, our understanding of physics, based on Einstein's theory of relativity, asserts that nothing can travel faster than the speed of light in a vacuum. This limitation poses a significant challenge when considering the vast distances between stars and galaxies. Even at light speed, it would take over 4 years to reach the nearest star, Proxima Centauri, and thousands, or even millions, of years to reach more distant stars or galaxies. This has led many scientists and theorists to explore alternative methods of space travel that could circumvent these limitations. One such possibility is the concept of wormholes. A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical tunnel-like structure that connects two separate points in space-time. In theory, a wormhole could allow for instantaneous travel between distant regions of space. While wormholes are consistent with general relativity, they remain purely theoretical at this point, as no evidence of their existence has been found. Additionally, if they do exist, there are significant challenges to making them traversable. Most models suggest that a wormhole would be highly unstable and would require some form of exotic matter, substances with negative energy, or mass, to keep it open long enough for travel. Another speculative concept is warp drive, a form of faster-than-light travel popularized by science fiction, particularly in Star Trek. The basic idea of warp drive involves compressing space in front of a spacecraft and expanding it behind, creating a bubble of spacetime that allows the ship to effectively move faster than light without violating the laws of physics. In 1994, Mexican physicist Miguel Alcubierre proposed a theoretical model for warp drive based on general relativity, known as the Alcubierre drive. However, this model also requires exotic matter to function, and the amount of energy required would be astronomical, far beyond our current technological capabilities. Despite these challenges, the possibility of faster-than-light travel continues to captivate the imaginations of scientists and the general public alike. The ability to travel to distant stars and galaxies would not only revolutionize space exploration but also open up new possibilities for colonization, resource acquisition, and perhaps even contact with other intelligent civilizations. It remains one of the great mysteries of space whether such advanced technologies will ever become a reality, or if they will remain confined to the realm of science fiction. In addition to faster-than-light travel, another profound mystery of space is the question of the ultimate fate of the universe. As mentioned earlier, the universe is expanding, with galaxies moving away from each other at ever-increasing speeds. This expansion is driven by dark energy, a mysterious force that makes up approximately 68% of the universe. While dark energy is currently accelerating the expansion of the universe, its long-term effects remain uncertain. One possibility is that the universe will continue to expand indefinitely, leading to a scenario known as the heat death, or Big Freeze. In this scenario, the expansion would eventually cause all stars to burn out, galaxies to drift apart, and matter to decay into low-energy particles, leaving the universe cold, dark, and lifeless. This would represent the ultimate end of all activity in the cosmos, a stark and lonely fate. Another potential outcome is the Big Crunch. In this scenario, the expansion of the universe would eventually slow down and reverse, causing galaxies to collide and merge as the universe contracts. This contraction would culminate in all matter collapsing into a single point, similar to the conditions of the Big Bang. Some theorists speculate that this could lead to a new Big Bang, with the universe being reborn in a cyclical process of expansion and contraction. A third possibility is the Big Rip. in which dark energy continues to accelerate the expansion of the universe at an ever-increasing rate. In this scenario, the expansion would eventually become so extreme that it would tear apart galaxies, stars, planets, and even atoms themselves. The fabric of space-time would be ripped apart, resulting in the complete disintegration of the universe. The ultimate fate of the universe depends on the properties of dark energy, which remain poorly understood. Observations of distant supernovae and the cosmic microwave background have provided some clues, but more data is needed to determine whether the universe will end in a big freeze, big crunch, big rip, or some other process entirely. The idea of the universe having a finite lifespan also raises philosophical and existential questions. What does it mean for human existence if the universe is destined to end in such a dramatic way? Can anything we do truly matter in the grand scheme of cosmic time? These questions have been debated by scientists, philosophers, and theologians for centuries, and they continue to inspire deep reflection on the nature of life, time, and the cosmos. In recent years, another mysterious aspect of space has emerged from the study of black holes. Black holes are regions of space where gravity is so strong that not even light can escape. They form when massive stars collapse under their own gravity, creating a singularity, a point of infinite density and zero volume, surrounded by an event horizon, beyond which nothing can escape. While black holes have been studied for decades, they remain one of the most puzzling and enigmatic objects in the universe. One of the biggest mysteries surrounding black holes is the nature of the singularity itself. According to general relativity, the singularity is a point where space-time curvature becomes infinite, and the known laws of physics break down. However, this creates a paradox, as the singularity cannot be described by our current understanding of gravity or quantum mechanics. Another mystery of black holes is the information paradox. According to quantum mechanics, information about the state of a physical system cannot be lost. However, when matter falls into a black hole, it seems to disappear beyond the event horizon, leading to the question of what happens to the information contained within that matter. Does it remain inside the black hole, or is it destroyed? This paradox has led to intense debates among physicists, with some proposing that information is preserved in the form of soft hair on the event horizon, while others suggest that it may be stored in a holographic manner on the surface of the black hole. In 2019, the first ever image of a black hole was captured by the Event Horizon Telescope, providing a groundbreaking look at the shadow of a supermassive black hole in the center of the galaxy M87. This image confirmed some aspects of Einstein's theory of general relativity, and has opened up new avenues for studying these mysterious objects. However, many questions remain, and black holes continue to challenge our understanding of gravity, quantum mechanics, and the nature of reality itself. Black holes are also connected to another profound mystery of space, the nature of time. According to general relativity, time slows down near massive objects like black holes due to the warping of space-time. This phenomenon, known as time dilation, means that time passes more slowly for an observer near a black hole than for someone far away. In extreme cases, such as near the event horizon of a black hole, time could effectively come to a standstill. This raises fascinating questions about the nature of time and how it relates to the structure of the universe. Time dilation is not limited to black holes. It also occurs in less extreme environments, such as near massive planets or stars, and it has been confirmed by experiments on Earth, such as those involving precise atomic clocks placed at different altitudes. However, the idea that time can flow at different rates depending on one's location in the universe challenges our intuitive understanding of time as a constant and uniform progression. These concepts become even more mind-bending when we consider the possibility of time travel. While time travel to the future is theoretically possible due to time dilation, astronauts traveling at near-light speeds could return to Earth having aged less than those who remain behind. Traveling to the past presents far greater challenges. Many physicists believe that time travel to the past would violate causality, leading to paradoxes such as the famous grandfather paradox, in which a time traveler prevents their own existence by altering the past. Nevertheless, some theoretical models allow for the possibility of time loops or closed time-like curves, in which time travel to the past could occur without violating causality. These ideas remain speculative, but they highlight the deep and unresolved mysteries of time and its relationship to space. As we continue to explore the mysteries of space, time remains one of the most perplexing and captivating concepts. Our understanding of time is intimately connected to space through the theory of relativity, yet it also transcends the tangible, posing deep philosophical questions about the nature of existence and the universe itself. One of the most compelling questions is whether time had a beginning and whether it will have an end. This takes us back to the Big Bang, the widely accepted theory that the universe began as a singularity around 13.8 billion years ago. The Big Bang theory describes the rapid expansion of the universe from an incredibly hot and dense state. In the earliest moments after the Big Bang, the universe was a chaotic and unimaginably dense mass of energy and particles, and as it expanded, matter began to cool and form the building blocks of the universe we know today. While this theory is supported by a wealth of observational evidence, such as the cosmic microwave background radiation and the redshift of distant galaxies, it still leaves many questions unanswered. For instance, what caused the Big Bang in the first place? Was it the beginning of time, or was there something before it? Some theories suggest that the Big Bang might not have been the absolute beginning, but rather a transition from a previous phase of the universe. One such theory is the idea of a Big Bounce, in which the universe goes through cycles of expansion and contraction. In this scenario, the Big Bang was not a singular beginning, but simply the latest iteration in a series of bounces. This model implies that the universe could have an infinite past and an infinite future, with no true beginning or end. Another speculative idea is that our universe is just one of many in a vast multiverse. The multiverse hypothesis suggests that there could be an infinite number of universes, each with its own laws of physics, dimensions, and histories. In this view, the Big Bang could have been the result of interactions between different universes or the formation of a new universe from the quantum foam of a larger multiverse. This idea, while highly speculative, is supported by some interpretations of quantum mechanics and string theory, which allow for the existence of multiple dimensions and parallel universes. The multiverse theory raises profound questions about the nature of reality. If there are countless other universes, could there be versions of ourselves living different lives in parallel worlds? Could some universes have entirely different physical laws, where concepts like time, space, and gravity operate in ways we cannot even imagine? These questions stretch the limits of our understanding and challenge the very notion of a single, unified reality. Yet, despite these intriguing possibilities, the multiverse theory remains purely theoretical at this point, with no direct observational evidence to support it. Proving or disproving the existence of other universes may be beyond our current scientific capabilities, but the idea continues to inspire new ways of thinking about the cosmos and our place within it. The question of whether time had a beginning also leads to deeper philosophical and metaphysical considerations. If time did begin with the Big Bang, what does that imply about the nature of causality? In our everyday experience, events are caused by preceding events, creating a chain of cause and effect that stretches back through time. But if time itself had a starting point, what caused that? Some thinkers propose that the concept of cause and effect might not apply to the universe's origin, suggesting that our understanding of causality may be incomplete or even irrelevant in the context of the universe as a whole. This brings us to the concept of time as a human construct. While time seems to be an inherent feature of the universe, some philosophers argue that our perception of time is shaped by our consciousness and the way we experience reality. In this view, time may not be an objective property of the universe, but rather a way for our minds to make sense of change and motion. This idea aligns with certain interpretations of quantum mechanics, where time behaves differently on the microscopic scale, leading to the possibility that time itself may be an emergent property of more fundamental processes. Quantum mechanics, in general, introduces a host of other mysteries related to the nature of space and time. At the quantum level, particles can exist in multiple states simultaneously, a phenomenon known as superposition, and can be entangled in such a way that the state of one particle is instantly correlated with the state of another, regardless of the distance between them. This has led to the concept of quantum non-locality, where events in one part of the universe can affect events in another part instantly, seemingly violating the speed of light limit set by relativity. One of the most famous experiments illustrating the strange behavior of quantum particles is the double-slit experiment, in which particles such as electrons or photons are fired at a barrier with two slits. When observed, the particles behave like individual objects, passing through one slit or the other. But when not observed, they exhibit wave-like behavior, creating an interference pattern that suggests they pass through both slits simultaneously. This raises profound questions about the role of the observer in shaping reality and the nature of consciousness itself. Some interpretations of quantum mechanics suggest that the act of observation is what collapses a particle's wave function, forcing it into a definite state. This has led to speculation that consciousness might play a fundamental role in the nature of reality, an idea explored in theories such as the many worlds interpretation and the participatory universe, concept proposed by physicist John Archibald Wheeler. In the many worlds interpretation, every possible outcome of a quantum event actually occurs, with each outcome creating a new branch of the universe. In this view, the universe is constantly splitting into an infinite number of parallel realities, with each one representing a different possibility. These ideas are not without controversy, and the nature of quantum mechanics remains one of the most profound mysteries in physics. The idea that reality might not be fixed but instead shaped by observation or consciousness challenges our deepest intuitions about the world around us. It also raises questions about the nature of free will and determinism. If every possible outcome is realized in some branch of the multiverse, does that mean that all events are predetermined, with every choice we make simply playing out in one universe or another? Or does the act of observation give us the power to shape reality in a meaningful way? In addition to the mysteries of quantum mechanics, space itself is full of phenomena that defy explanation. One such enigma is dark matter, an invisible substance that makes up about 27% of the universe's mass-energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it impossible to detect directly. However, its presence is inferred from its gravitational effects on visible matter, such as the rotation of galaxies and the bending of light from distant stars. Despite decades of research, the true nature of dark matter remains elusive. Various candidates for dark matter particles have been proposed, including weakly interacting massive particles, WIMPs, and axions, but none have been definitively detected. Some theories suggest that dark matter could be made up of exotic particles that interact only through gravity and the weak nuclear force, while others propose that our understanding of gravity itself might need to be modified to account for the observed effects. The mystery of dark matter is closely tied to the mystery of dark energy, which, as mentioned earlier, is responsible for the accelerated expansion of the universe. Together, dark matter and dark energy make up about 95% of the universe's total mass energy content, yet we know almost nothing about them. This has led some scientists to suggest that we may be missing a fundamental aspect of physics, and that our current theories of gravity and cosmology may need to be revised or extended to explain these phenomena. The search for dark matter and dark energy continues, with experiments being conducted both on Earth and in space to try to detect these elusive substances. However, it remains one of the greatest unsolved mysteries of space, and it may take decades, if not longer, to fully unravel. As we explore these mysteries, it's clear that space is not only a physical frontier but also a philosophical one. The questions raised by the nature of space, time, and reality challenge our understanding of the universe and our place within it. Whether we are grappling with the mind-bending implications of quantum mechanics, the search for dark matter and dark energy, or the possibility of multiple universes, the study of space pushes the boundaries of human knowledge and imagination. Our journey through the mysteries of space is far from over, and as we push further into the unknown, the more we realize how much is left to discover. One of the most fascinating and perplexing areas of study is the concept of black holes. These enigmatic regions of space-time are known for their ability to trap everything within them, including light, which is why they appear black. But black holes are far more than just cosmic vacuums. They hold the key to some of the deepest questions about gravity, quantum mechanics, and the ultimate fate of the universe. Black holes form when massive stars collapse under their own gravity at the end of their life cycle, compressing their matter into a singularity, a point of infinite density where the laws of physics, as we currently understand them, break down. Surrounding the singularity is the event horizon, a boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. Once something crosses the event horizon, it is lost to the black hole forever. The formation of black holes itself presents a series of mysteries. While we have a decent understanding of how stellar mass black holes come into being through the collapse of massive stars, there are other types of black holes that raise significant questions. For example, supermassive black holes, which are millions to billions of times more massive than the Sun, are found at the centers of most galaxies, including our own Milky Way. The mystery is how these supermassive black holes formed and grew to such immense sizes so early in the universe's history. One theory suggests that supermassive black holes formed from the direct collapse of large clouds of gas in the early universe, bypassing the need for a stellar progenitor. Another possibility is that smaller black holes merged over time to form larger ones. However, observations of quasars, extremely bright and distant objects powered by supermassive black holes, indicate that some of these black holes were already enormous when the universe was less than 1 billion years old. This challenges our current understanding of how black holes grow and evolve. Adding to the mystery is the recent discovery of intermediate mass black holes, which are thought to bridge the gap between stellar mass and supermassive black holes. These black holes are difficult to detect because they don't fit neatly into either category, and very few have been observed. Understanding how intermediate mass black holes form and interact with their environments could provide crucial insights into the life cycle of black holes and the structure of galaxies. While black holes are often thought of as destroyers, they may also play a creative role in the universe. For example, the intense gravitational forces around black holes can drive the formation of stars by compressing gas in their vicinity. Additionally, the accretion disks of matter that spiral into black holes can generate powerful jets of energy, which can influence the evolution of entire galaxies. In this way, black holes are not just passive objects, but active participants in the cosmic drama. One of the most famous black holes in modern astronomy is the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. Despite its massive size, it is relatively quiet compared to the supermassive black holes found in more active galaxies. Observations of the stars orbiting Sagittarius A* have provided some of the most compelling evidence for the existence of black holes and have allowed scientists to measure its mass with great precision. However, Sagittarius A* occasionally flares up with bursts of X-rays, raising questions about the nature of its activity and the behavior of matter near the event horizon. In recent years, black holes have taken center stage in some of the most groundbreaking discoveries in physics. In 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration made the first direct detection of gravitational waves, ripples in spacetime caused by the collision of two black holes. This discovery confirmed a key prediction of Einstein's general theory of relativity and opened up a new way of observing the universe. Gravitational waves allow us to listen to cosmic events that are invisible to traditional telescopes, such as the merger of black holes and neutron stars. But black holes also pose profound questions for the nature of information and the fabric of reality itself. One of the most famous paradoxes associated with black holes is the information paradox, which arises from the conflict between general relativity and quantum mechanics. According to general relativity, anything that falls into a black hole is lost forever, including the information about its physical state. However, quantum mechanics dictates that information cannot be destroyed. This paradox has puzzled physicists for decades and has led to various hypotheses, including the idea that information might be encoded in the event horizon or that it could escape through Hawking radiation. Hawking radiation, proposed by physicist Stephen Hawking in 1974, is a theoretical process by which black holes can slowly lose mass and eventually evaporate. This occurs because, according to quantum mechanics, pairs of virtual particles are constantly being created and annihilated near the event horizon. Occasionally, one of these particles falls into the black hole while the other escapes, effectively stealing energy from the black hole and causing it to shrink over time. While Hawking radiation has not yet been observed, it remains a key concept in our understanding of black holes and the ultimate fate of these mysterious objects. The information paradox and Hawking radiation highlight the fundamental tension between general relativity, which governs large-scale cosmic structures, and quantum mechanics, which describes the behavior of particles on the smallest scales. Unifying these two theories into a single theory of everything is one of the greatest challenges in modern physics. Some believe that black holes may hold the key to resolving this conflict, as they represent extreme environments where both general relativity and quantum effects are at play. Another tantalizing mystery surrounding black holes is the idea of wormholes, theoretical passages through spacetime that could connect distant points in the universe. Wormholes are solutions to Einstein's equations of general relativity, but they require exotic forms of matter with negative energy to remain stable. While there is no direct evidence for the existence of wormholes, they have captured the imagination of scientists and science fiction writers alike as potential shortcuts through space and time. Some theories even suggest that black holes could be gateways to other universes or dimensions, although this remains highly speculative. Speaking of other dimensions, the concept of higher dimensions is another mystery that arises from modern theories of physics, particularly string theory. String theory posits that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy. To make the mathematics of string theory work, it requires the existence of additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. These extra dimensions are thought to be compactified, or curled up, so that they are too small to detect directly. If higher dimensions do exist, they could provide explanations for some of the unsolved mysteries of space, such as the nature of dark matter or the unification of gravity with the other fundamental forces. However, testing these ideas is incredibly difficult, and string theory remains a highly speculative and controversial area of research. Nonetheless, the possibility that the universe contains hidden dimensions adds yet another layer of intrigue to the mysteries of space. As we explore these profound questions, it's important to remember that our understanding of the universe is constantly evolving. New discoveries, such as the detection of gravitational waves, the study of exoplanets, and the observation of distant galaxies, are continually reshaping our view of the cosmos. The mysteries of space challenge us to think beyond the limits of our current knowledge and to embrace the unknown with curiosity and wonder. From the enigmatic nature of black holes to the possibility of multiple universes, from the origins of the cosmos to the fate of time itself, the mysteries of space are as vast and boundless as the universe they inhabit. These questions push the boundaries of human understanding and inspire us to explore the universe not only with telescopes and satellites, but also with our minds and imaginations. As we continue to explore the vast and endless mysteries of space, we find ourselves confronted with some of the most intriguing questions about the fabric of reality itself. One such mystery involves the concept of dark matter and dark energy, 2 elusive components that together make up about 95% of the universe, yet remain largely invisible and undetectable to us. Dark matter is believed to be responsible for the missing mass in galaxies, as observed by astronomers for decades. When we look at galaxies, the stars and gas we can see do not have enough mass to account for the gravitational forces holding them together. Without this extra mass, galaxies should fly apart. However, something invisible is providing the necessary gravitational pull to keep these galaxies intact. This invisible substance is what scientists have dubbed dark matter. The problem with dark matter is that we can't see it, detect it directly, or interact with it in any way other than through its gravitational effects. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it impossible to observe through traditional telescopes. Yet, it is thought to make up about 27% of the universe's total mass energy content. Scientists have devised numerous experiments to try to detect dark matter particles, but so far, these efforts have come up empty. One theory about dark matter is that it could consist of exotic particles that do not interact with electromagnetic forces like ordinary matter does. These hypothetical particles are known as WIMPs, weakly interacting massive particles, or axions, both of which are currently being searched for in particle physics experiments. Alternatively, some theories propose that dark matter could be made up of primordial black holes, tiny black holes that formed in the early universe. However, no definitive evidence for any of these candidates has yet been found. The existence of dark matter is supported by a range of observations, from the rotation curves of galaxies to the gravitational lensing of light around massive objects. Gravitational lensing occurs when light from a distant object is bent by the gravitational field of a massive intervening object, creating a magnified or distorted image of the background source. In some cases, the amount of lensing observed cannot be explained by the visible matter alone, suggesting the presence of dark matter. But dark matter is only part of the puzzle. Even more mysterious is dark energy, a force that is driving the accelerated expansion of the universe. In the late 1990s, astronomers studying distant supernovae made the surprising discovery that the expansion of the universe is not slowing down, as had been expected, but is actually speeding up. This discovery led to the idea that some form of energy, now called dark energy, is pushing galaxies apart at an ever-increasing rate. Dark energy is even more enigmatic than dark matter because we have no idea what it is made of or how it works. One possibility is that dark energy is a property of space itself, as suggested by Einstein's cosmological constant. According to this idea, as space expands, more dark energy is created, leading to the accelerated expansion of the universe. Another possibility is that dark energy could be related to a new and unknown force or field that permeates the cosmos. The discovery of dark energy has profound implications for the ultimate fate of the universe. If dark energy continues to drive the accelerated expansion, the universe could continue to expand forever, eventually reaching a state known as the Big Freeze. In this scenario, galaxies would drift apart, stars would burn out, and the universe would become a cold, dark, and empty place. Alternatively, if dark energy changes over time, it could lead to different outcomes, such as a Big Rip, where the expansion becomes so extreme that galaxies, stars, and even atoms are torn apart. The nature of dark matter and dark energy is one of the biggest unsolved mysteries in cosmology, and solving it could revolutionize our understanding of the universe. These phenomena challenge our current models of physics and force us to rethink fundamental concepts such as gravity, energy, and the structure of space and time. In addition to dark matter and dark energy, another fascinating mystery of space involves the origin and fate of the universe itself. The prevailing theory of the universe's origin is the Big Bang theory, which proposes that the universe began as a hot, dense point approximately 13.8 billion years ago, and has been expanding ever since. However, the Big Bang theory raises its own set of questions. What caused the Big Bang? What existed before it? And will the universe eventually come to an end, or will it continue expanding indefinitely? One hypothesis about the universe's beginning is the idea of cosmic inflation, which suggests that in the first fraction of a second after the Big Bang, the universe underwent a rapid and exponential expansion. This inflationary period would have smoothed out any irregularities in the early universe, leading to the relatively uniform distribution of matter and energy we observe today. Inflation also predicts the existence of tiny quantum fluctuations that would eventually grow into the galaxies, stars, and planets we see today. While cosmic inflation is widely accepted by many scientists, it is not without its challenges. For example, we don't know what caused inflation or what ended it. Moreover, some versions of inflationary theory suggest that inflation could have occurred in different regions of space at different rates, leading to the idea of a multiverse, a collection of many universes, each with its own physical laws and constants. If the multiverse exists, our universe could be just one of many, raising profound philosophical and scientific questions about the nature of reality and our place in it. The fate of the universe is another area of intense speculation. As mentioned earlier, if dark energy continues to dominate, the universe could end in a big freeze or a big rip. However, other possibilities exist. One is the Big Crunch, in which the expansion of the universe eventually slows down and reverses, causing the universe to collapse in on itself. This scenario would lead to a final, catastrophic event similar to the Big Bang but in reverse. Another possibility is the Big Bounce, in which the universe undergoes a cycle of expansion and contraction, with each cycle leading to a new Big Bang. The question of the universe's fate is closely tied to the nature of time itself. In our everyday experience, time seems to flow in one direction, from the past to the future. However, the laws of physics, particularly in the realm of quantum mechanics and relativity, do not necessarily distinguish between past and future. This has led some scientists to suggest that time may not be as straightforward as it appears, and that the arrow of time could be an emergent property of the universe, rather than a fundamental aspect of reality. One of the most mind-bending ideas about time is the concept of time loops, or closed time-like curves, which arise in some solutions to Einstein's equations of general relativity. These time loops would allow for the possibility of traveling back in time, creating paradoxes such as the grandfather paradox, in which a time traveler could potentially prevent their own existence by altering the past. While time travel remains speculative, the study of time and its relationship to space is an ongoing area of research in theoretical physics. As we delve deeper into the mysteries of space, we must also consider the possibility of life beyond Earth. The search for extraterrestrial life has been a central focus of space exploration for decades, and recent discoveries have only heightened the sense of excitement and urgency in this quest. One of the most promising places to search for life is within our own solar system. Several moons of the gas giants Jupiter and Saturn are thought to harbor subsurface oceans of liquid water, protected from the harsh conditions of space by thick ice crusts. For example, Europa, one of Jupiter's moons, has a global ocean beneath its icy surface that may contain more water than all of Earth's oceans combined. Similarly, Saturn's moon Enceladus has been observed ejecting plumes of water vapor and ice particles from its southern pole, suggesting the presence of an ocean beneath its icy shell. These subsurface oceans could provide the necessary conditions for life, particularly if they contain hydrothermal vents similar to those found on Earth's ocean floor. On Earth, these vents are home to diverse ecosystems of organisms that thrive in the absence of sunlight, relying on chemical reactions to produce energy. If similar conditions exist on Europa or Enceladus, it is possible that microbial life could be present in these alien oceans. Beyond the solar system, the discovery of exoplanets, planets orbiting stars outside our solar system, has revolutionized our understanding of the potential for life elsewhere in the universe. Since the first confirmed exoplanet was discovered in 1992, thousands of exoplanets have been found, many of them in the habitable zone of their parent stars, where conditions could be right for liquid water to exist. Some of these exoplanets are thought to be rocky, like Earth, and could have atmospheres capable of supporting life. The search for exoplanets and the study of their atmospheres is a rapidly growing field, with new missions such as the James Webb Space Telescope and the Transiting Exoplanets Survey Satellite, TESS, providing unprecedented data on these distant worlds. By studying the chemical composition of exoplanet atmospheres, scientists hope to detect biosignatures, chemical markers that could indicate the presence of life, such as oxygen, methane, or water vapor. As we continue our exploration of the possibilities for extraterrestrial life, the search for biosignatures is a crucial aspect of astrobiology, the study of life in the universe. One of the most tantalizing targets in this quest is Mars, our neighboring planet. Mars has long been a focal point of exploration due to its similarities to Earth and the evidence that liquid water once flowed on its surface. Recent missions, such as NASA's Perseverance rover, are actively searching for signs of ancient microbial life and collecting samples that may one day return to Earth for detailed analysis. The presence of methane in the Martian atmosphere has sparked particular interest, as methane can be produced by biological processes. While geological processes can also create methane, its intermittent detection suggests that it might be generated by active processes, possibly linked to subsurface microbial life. Understanding the history of water on Mars and the planet's past climate is essential to evaluating its habitability and the potential for life, both past and present. However, Mars is not the only body in our solar system with intriguing prospects for life. Titan, Saturn's largest moon, presents a different but equally captivating environment. Titan has a thick atmosphere rich in organic compounds and features rivers and lakes of liquid methane and ethane on its surface. The presence of these hydrocarbons raises questions about the potential for life forms that could utilize methane as a solvent, in stark contrast to life as we know it, which relies on water. The study of extremophiles, organisms that thrive in extreme conditions on Earth, provides insights into the potential for life in hostile environments elsewhere. For instance, certain bacteria can survive in acidic hot springs, while others can endure extreme pressure in deep-sea hydrothermal vents. These discoveries challenge our definitions of life and expand the search for extraterrestrial organisms to environments that might initially seem uninhabitable. The quest for extraterrestrial intelligence, SETI, adds another dimension to our exploration of life beyond Earth. Scientists involved in SETI use various methods to search for signals from advanced civilizations. This involves monitoring radio frequencies and searching for patterns that could indicate intelligent communication. The vastness of space and the sheer number of stars and planets suggest that we are not alone in the universe. But the question remains, if there are other civilizations, why haven't we found them yet? This dilemma, often referred to as the Fermi paradox, raises important considerations about the nature of intelligent life. One possibility is that intelligent civilizations are exceedingly rare, and the conditions necessary for their development are not easily replicated. Another theory suggests that advanced civilizations may be self-destructive, falling victim to technological or environmental crises before they can establish communication across interstellar distances. Alternatively, it's possible that advanced civilizations are deliberately avoiding contact, adhering to a prime directive of non-interference with less advanced societies, similar to the ethics portrayed in science fiction. This perspective raises profound questions about the nature of intelligence, morality, and our place in the cosmos. If we are indeed alone or isolated in the vast universe, what does that imply about humanity's role in the grand scheme of existence? The mystery of dark energy also intersects with our exploration of life in the universe. As we ponder the expansion of the cosmos, we must consider how it affects the potential for life to exist elsewhere. The accelerated expansion driven by dark energy suggests that the universe will continue to evolve in ways we may not fully understand. Over cosmic timescales, galaxies will drift apart, and the conditions for life may change dramatically. As we contemplate these mysteries, the search for extraterrestrial life and the exploration of the universe are more than just scientific endeavors. They reflect our deep-seated desire to understand our origins, our future, and the nature of existence itself. The questions raised by the mysteries of space push us to consider not only the physical universe but also the philosophical implications of our discoveries. In addition to these questions about life and existence, the study of cosmic phenomena continues to captivate our imagination. One of the most profound phenomena is the nature of time and how it interacts with space. Time is not merely a backdrop against which events occur. It is intricately linked to the fabric of the universe. Einstein's theory of relativity fundamentally changed our understanding of time, showing that it is relative and can be affected by gravity and speed. According to relativity, time can pass at different rates depending on the observer's velocity and gravitational field. For example, time moves slightly slower in stronger gravitational fields, a phenomenon confirmed by experiments involving atomic clocks placed at different altitudes. This means that an astronaut aboard the International Space Station, who experiences less gravitational pull than someone on Earth, ages ever so slightly more slowly, a concept known as time dilation. The implications of time dilation extend beyond the realm of physics. They touch on existential questions about the nature of reality and our perception of time. If time can be manipulated, what does that mean for our understanding of causality and the sequence of events in the universe? As we delve deeper into these concepts, we are confronted with the possibility that our perception of time may be limited by our human experience. Another captivating aspect of the universe is the phenomenon of cosmic inflation, which describes the rapid expansion of the universe in its earliest moments. The idea of inflation addresses several puzzles within the Big Bang theory, such as the uniformity of the cosmic microwave background radiation. The inflationary model proposes that the universe underwent exponential growth, smoothing out irregularities and leading to the large-scale structure we observe today. Inflation also suggests that the universe could be much larger than what we can currently observe, perhaps infinite in extent. This raises profound questions about the nature of the universe and whether it is part of a larger multiverse. If our universe is just one bubble in a vast sea of universes, each with different physical laws and constants, then the implications for our understanding of reality are staggering. The study of cosmic inflation and the potential multiverse challenges our notions of reality and existence, compelling us to reconsider our place in the grand scheme of things. As we explore these mysteries, we are reminded that the universe is not just a collection of celestial objects. It is a dynamic, ever-evolving tapestry of events, forces, and possibilities. Our fascination with the mysteries of space is intertwined with our quest for knowledge and understanding. The pursuit of answers to these questions drives scientific exploration and technological advancement, leading to new discoveries and insights that expand our horizons. As we launch missions to distant planets, observe the cosmic microwave background, and explore the behavior of black holes, we push the boundaries of our understanding and redefine what is possible. In this endeavor, collaboration across disciplines is essential. The challenges of understanding the universe require not only physicists and astronomers but also mathematicians, chemists, biologists, and philosophers. Interdisciplinary approaches enable us to tackle complex problems from multiple angles, fostering innovative solutions and new ways of thinking. As we continue to probe the mysteries of space, we are also faced with ethical considerations regarding our exploration efforts. The search for extraterrestrial life, the potential for colonization of other planets, and the preservation of our own planet raise important questions about responsibility and stewardship. The actions we take today will shape the future of humanity and the universe, and we must approach our exploration with a sense of humility and respect for the unknown. In conclusion, the mysteries of space are not just scientific inquiries. They are reflections of our deepest curiosities and existential ponderings. From the enigma of dark matter and dark energy to the potential for a life beyond Earth and the nature of time itself, each mystery invites us to contemplate our place in the cosmos. As we stand on the precipice of discovery, we must embrace the unknown with open minds and hearts, ready to explore the wonders that lie beyond our world. The journey through the mysteries of space is ongoing, and as we continue to seek answers, we are reminded that the universe is a vast, intricate puzzle waiting to be unraveled. Each discovery, each insight, brings us closer to understanding the fundamental nature of reality, and in this pursuit, we find not only knowledge but also a profound sense of wonder and connection to the cosmos. The questions may be infinite, but so too is our capacity for exploration and understanding. With every star we gaze upon and every cosmic phenomenon we study, we are reminded of the beauty and complexity of the universe, a tapestry woven from the threads of time, space, and possibility. As we continue to delve into the profound mysteries of space, it's essential to recognize how our understanding of the universe has evolved over centuries. From ancient civilizations who looked to the stars with wonder and reverence, believing them to be the domain of the gods, to the modern scientific approach that seeks empirical evidence and understanding, our journey has been transformative. The early astronomers, such as Copernicus, Galileo, and Kepler, laid the groundwork for a heliocentric model of the solar system, challenging the long-held geocentric views. Their work opened the door to a deeper understanding of celestial mechanics and the nature of our place within the cosmos. Galileo's use of the telescope not only revealed the moons of Jupiter but also provided critical evidence for the Copernican model, forever changing humanity's perspective on the universe. As we moved into the 20th century, the advent of modern physics brought forth revolutionary ideas. Einstein's theory of relativity transformed our understanding of space and time, revealing that they are intertwined in a four-dimensional continuum. His famous equation, E equals mc squared, established a connection between mass and energy, laying the groundwork for nuclear physics and our understanding of stellar processes. With the development of quantum mechanics, we entered a new realm of understanding the microcosm. This field of physics introduced concepts that defy classical intuition, such as superposition and entanglement, challenging our fundamental understanding of reality. Quantum mechanics not only describes the behavior of particles at the smallest scales but also plays a critical role in the functioning of the universe as a whole, influencing phenomena from the formation of atoms to the behavior of black holes. The exploration of black holes is one of the most fascinating aspects of modern astrophysics. Once regarded as mere theoretical constructs, black holes are now understood to be real astronomical objects, formed when massive stars collapse under their own gravity. The region surrounding a black hole, known as the event horizon, represents a boundary beyond which nothing can escape, not even light. This makes black holes among the most enigmatic and extreme environments in the universe. The study of black holes has profound implications for our understanding of gravity and the fabric of space-time. One of the most significant revelations in recent years is the detection of gravitational waves, ripples in space-time caused by the merging of black holes. The first detection in 2015 confirmed a prediction made by Einstein a century earlier and opened a new window for observing cosmic events. Gravitational wave astronomy allows us to probe the universe in ways previously thought impossible, offering insights into the life cycles of stars and the dynamics of galactic collisions. Moreover, black holes challenge our understanding of the fundamental laws of physics. The question of what happens at the singularity, the point of infinite density at the center of a black hole, remains unresolved. Current theories, including general relativity and quantum mechanics, struggle to reconcile their differences in this extreme regime. This gap in our understanding has led to ongoing research in the quest for a theory of quantum gravity, which would unify these fundamental forces and potentially unlock deeper insights into the workings of the universe. As we navigate the complexities of space, we also encounter the fascinating concept of cosmic microwave background radiation, CMB. This relic radiation, a remnant of the early universe, provides a snapshot of the cosmos approximately 380,000 years after the Big Bang. The CMB is uniform, with slight fluctuations that reveal the density variations that ultimately led to the formation of galaxies and large-scale structures. Studying the CMB has provided remarkable evidence supporting the Big Bang theory and has refined our understanding of the universe's age, composition, and expansion rate. The detailed measurements of the CMB, particularly from missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, have shed light on fundamental questions about the universe's history and its future evolution. Another intriguing aspect of space exploration is the role of cosmic phenomena in shaping planetary systems. The discovery of exoplanets has sparked a revolution in our understanding of how planetary systems form and evolve. Utilizing techniques such as the transit method, where a planet passes in front of its star, and the radial velocity method, which detects wobbles in stars caused by orbiting planets, astronomers have identified thousands of exoplanets, many of which exist in their star's habitable zone. The diversity of these exoplanets, ranging from gas giants to rocky worlds, has challenged previous models of planetary formation. Some exoplanets exhibit unusual characteristics, such as extreme weather, tidal locking, and eccentric orbits. Studying these worlds not only informs our understanding of how our solar system formed but also raises questions about the potential for diverse forms of life in the universe. The search for habitable environments extends beyond exoplanets to moons within our own solar system. As previously mentioned, bodies like Europa and Enceladus show promise due to their subsurface oceans, but other moons such as Ganymede and Titan also warrant exploration. Ganymede, the largest moon in the solar system, is believed to possess a salty ocean beneath its icy surface, while Titan's dense atmosphere and liquid hydrocarbon lakes offer a unique environment that could harbor life in unexpected forms. The exploration of these celestial bodies is not merely an academic exercise, it has practical implications for our understanding of life's resilience and adaptability. By studying extreme environments on Earth, such as hydrothermal vents and acidic lakes, we gain insights into the potential for life in harsh conditions elsewhere. This interdisciplinary approach emphasizes the interconnectedness of planetary science, biology, and astrobiology, paving the way for future discoveries. As we push the boundaries of exploration, we must also grapple with the ethical considerations of our actions in space. The question of planetary protection has become increasingly relevant as we contemplate sending missions to potentially habitable worlds. Ensuring that we do not contaminate other celestial bodies with Earth microbes is essential to preserving the integrity of those ecosystems and preventing any unintended consequences. Additionally, the prospect of human colonization of other planets raises ethical dilemmas about resource utilization, environmental stewardship, and the potential impact on indigenous ecosystems. As we expand our presence into the cosmos, we must do so with a sense of responsibility and respect for the diverse environments we encounter. Ultimately, the exploration of space is a reflection of humanity's quest for knowledge, understanding, and connection to the universe. The mysteries we uncover challenge our perceptions, ignite our imagination, and inspire future generations. Each discovery, whether it be the detection of gravitational waves, the study of exoplanets, or the search for extraterrestrial life, enriches our narrative and deepens our appreciation for the complexities of existence. As we reflect on the vastness of the universe and our place within it, we are reminded of the interconnectedness of all things. The stars that twinkle in the night sky have been a source of wonder and inspiration for countless generations, shaping philosophies and scientific pursuits. The questions that arise from our exploration are not just scientific inquiries. They resonate deeply with our human experience. In our quest to understand the cosmos, we come to realize that the universe is not a distant entity to be studied. It is an intricate tapestry woven with the threads of time, space, and possibility. Each celestial body, from the smallest asteroid to the largest galaxy, contributes to the grand narrative of the cosmos, inviting us to explore, question, and dream. As we look to the future, the potential for discovery remains boundless. New technologies and missions, such as the Artemis program, aim to return humans to the moon and establish a sustainable presence there. The long-term vision of crewed missions to Mars and beyond fuels our collective imagination and drives innovation in fields ranging from engineering to biology. Moreover, the rapid advancements in artificial intelligence and robotics open new frontiers for exploration. Autonomous spacecraft equipped with AI systems can analyze data in real time, make decisions, and adapt to unforeseen challenges, enhancing our ability to explore the most distant reaches of the universe. In closing, the mysteries of space serve as a reminder of our place within the cosmos, a tiny yet significant part of an intricate and ever-evolving universe. The questions we ask, the discoveries we make, and the stories we tell shape our understanding of reality and our connection to the greater whole. As we venture further into the unknown, we do so not just as explorers but as custodians of the knowledge and wonder that inspire our shared journey through the cosmos. In this grand narrative of exploration, the pursuit of understanding transcends individual accomplishments. It becomes a collective endeavor that unites humanity in our quest for meaning, connection, and discovery. The universe beckons us to continue our journey, to seek answers, and to embrace the mysteries that lie ahead, knowing that every step we take brings us closer to unlocking the secrets of the cosmos. As we further our exploration into the mysteries of space, we encounter a realm filled with phenomena that challenge our understanding of the universe and push the limits of human ingenuity. One such phenomenon is the concept of time travel, which has captured the imaginations of scientists and dreamers alike. While time travel often conjures images of science fiction, the theoretical underpinnings suggest that it may not be as far-fetched as it seems. According to Einstein's theory of relativity, time is not a constant. It can be stretched and compressed based on speed and gravity. This concept opens up the possibility of time dilation, where traveling at significant fractions of the speed of light could theoretically allow an individual to move forward in time. While this is currently beyond our technological capabilities, the exploration of high-speed travel, such as potential spacecraft powered by nuclear fusion or antimatter, keeps the door open for future possibilities. Moreover, the notion of wormholes presents another theoretical avenue for time travel. A wormhole, as described in general relativity, acts as a bridge between 2 points in spacetime. If such structures exist and could be stabilized, they might allow for instantaneous travel across vast distances or even backward in time. However, the practical challenges of creating and sustaining a traversable wormhole are immense, and current scientific understanding does not provide a clear path to their realization. As we ponder these intriguing concepts, we also grapple with the philosophical implications of time travel. The potential to change past events raises questions about free will, causality, and the nature of reality. Would altering a single event create a ripple effect, leading to unforeseen consequences? The grandfather paradox, where a time traveler could potentially prevent their own existence, highlights the complex interplay between time and causality. Such considerations remind us that our quest for understanding is not solely scientific. It is also deeply intertwined with our values, beliefs, and sense of identity. In addition to the mysteries of time, the study of dark matter remains one of the most pressing enigmas in astrophysics. Although dark matter makes up approximately 27% of the universe, it has yet to be directly observed. Its presence is inferred from gravitational effects on visible matter, such as galaxies and galaxy clusters. The rotational curves of galaxies, which do not align with the expected gravitational pull from visible matter, strongly suggest that dark matter exists and exerts a significant influence on the structure and evolution of the universe. Several candidates for dark matter have been proposed, including weakly interacting massive particles, WIMPs, and axions. Despite extensive searches using particle accelerators and underground detectors, no definitive evidence has yet been found. Understanding dark matter is critical, as it plays a fundamental role in galaxy formation and the overall dynamics of the universe. Another aspect of cosmic mystery involves the elusive nature of dark energy, which constitutes about 68% of the universe. Dark energy is thought to be responsible for the accelerated expansion of the cosmos, a discovery made in the late 1990s that took the scientific community by surprise. While the exact nature of dark energy remains unknown, theories range from the cosmological constant, a concept introduced by Einstein, to dynamic fields that evolve over time. The investigation of dark energy presents profound challenges, as it defies direct detection. Researchers utilize various observational techniques, such as supernova measurements and cosmic microwave background observations, to gather insights into its effects on the universe's expansion. Understanding dark energy not only sheds light on the fate of the universe but also raises questions about the fundamental forces that govern cosmic dynamics. As we explore these mysteries, we must also consider the role of technology in expanding our horizons. Advancements in observational tools, such as the Hubble Space Telescope, have revolutionized our understanding of the cosmos. Upcoming missions, including the James Webb Space Telescope, promise to provide unprecedented views of the universe, allowing scientists to study the formation of stars, galaxies, and potentially habitable planets in unprecedented detail. Furthermore, the development of new methodologies, such as machine learning and data analysis techniques, enables researchers to sift through vast amounts of astronomical data, uncovering patterns and insights that were previously unattainable. These innovations enhance our capacity to explore the universe and answer questions that have long eluded us. The quest to explore space is not merely about scientific discovery, it is also a journey of self-discovery. As we venture into the unknown, we confront fundamental questions about existence, purpose, and our connection to the cosmos. Each mission, each discovery, reminds us of our shared humanity and the universal quest for knowledge and understanding. In this context, the exploration of space also serves as a testament to human resilience and ingenuity. The challenges of space travel, from the harsh conditions of the vacuum to the psychological toll of long-duration missions, demand innovative solutions and unyielding determination. As we look toward the future, the potential for human settlement on other planets raises questions about sustainability, ethics, and the legacy we will leave for future generations. As we continue to unravel the mysteries of space, we are reminded that our journey is just beginning. The universe is vast, and the questions we ask will shape the course of our exploration. Each answer will likely lead to new questions, pushing us further into the depths of understanding and inspiring future generations to gaze at the stars and wonder. Ultimately, the mysteries of space invite us to embrace uncertainty and celebrate the unknown. The universe is a tapestry woven with the threads of countless stories, waiting to be uncovered. As we take each step into the cosmos, we do so with a sense of wonder, curiosity, and the realization that the quest for knowledge is a fundamental aspect of what it means to be human. In this grand exploration, we stand united as a species, connected by our shared curiosity and desire to understand the universe. As we gaze into the night sky, we are reminded that we are part of something greater, a cosmic journey that transcends time and space, inviting us to continue our exploration and seek answers to the profound mysteries that await us. With each passing moment, the universe reveals new secrets, and our understanding evolves. As we embark on this journey, we remain committed to the pursuit of knowledge and the exploration of the unknown, knowing that the mysteries of space will continue to inspire, challenge, and enrich our understanding of existence itself. As we delve deeper into the mysteries of space, we encounter the fascinating concept of cosmic inflation, a theory that attempts to explain the rapid expansion of the universe in its earliest moments. This phenomenon, believed to have occurred just fractions of a second after the Big Bang, suggests that the universe underwent exponential expansion, stretching from subatomic scales to macroscopic dimensions in an unimaginably short time. The theory of cosmic inflation addresses several puzzles inherent in the Big Bang model, such as the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. It posits that tiny quantum fluctuations during this inflationary period could have seeded the formation of galaxies and other cosmic structures we observe today. By studying the remnants of this early expansion, scientists aim to understand the initial conditions that led to the universe's current state. Inflationary theory not only deepens our understanding of the universe's infancy but also raises intriguing questions about the very nature of reality. The notion that our universe may be just one of many in a multiverse, each with its own set of physical laws and constants, challenges our perception of existence. This idea invites speculation about the potential for diverse forms of life across different universes, and the implications for our understanding of cosmology. As we explore these profound concepts, we must also consider the role of dark flow, a mysterious phenomenon that suggests our galaxy, along with others, is moving towards a massive gravitational force beyond our observable universe. Observations of galaxy clusters indicate a peculiar motion that cannot be easily explained by the gravitational pull of visible matter. This enigmatic motion raises questions about the structure of the universe and the influence of unobserved matter or forces on cosmic dynamics. The search for answers about dark flow leads us to the study of large-scale cosmic structures, such as galaxy superclusters and voids. These immense formations reveal the underlying architecture of the universe and provide insights into the distribution of matter and energy across cosmic distances. Understanding the interplay between these structures helps to refine our models of cosmology and provides clues to the universe's evolution. The exploration of space also encompasses the study of cosmic rays, high-energy particles originating from outside our solar system. These particles, traveling at nearly the speed of light, bombard the Earth and interact with our atmosphere, creating showers of secondary particles. Studying cosmic rays not only enhances our understanding of fundamental physics but also provides insights into astrophysical processes occurring in distant galaxies and supernovae. One of the most intriguing questions surrounding cosmic rays is their origin. While some are believed to originate from supernova remnants, others may be linked to more exotic sources, such as active galactic nuclei or gamma-ray bursts. Understanding these sources could unlock new knowledge about the extreme conditions present in the universe and the processes that accelerate particles to such incredible speeds. In addition to cosmic rays, the study of solar phenomena, such as solar flares and coronal mass ejections, reveals the dynamic nature of our Sun and its impact on the solar system. These explosive events can unleash vast amounts of energy and charged particles, affecting satellite communications, power grids, and even the Earth's magnetosphere. Understanding solar activity is crucial not only for safeguarding technology but also for comprehending the Sun's role in the broader cosmic context. As we broaden our exploration to include exoplanets and the search for extraterrestrial life, we must consider the factors that contribute to planetary habitability. The conditions necessary for life as we know it, liquid water, suitable temperatures, and a stable atmosphere, are often taken as prerequisites. However, the diversity of environments found in our solar system and beyond suggests that life could potentially arise in forms we have yet to imagine. The study of extremophiles, organisms that thrive in extreme conditions on Earth, provides valuable insights into the potential for life in harsh environments elsewhere in the universe. From deep-sea hydrothermal vents to acidic lakes, these resilient organisms challenge our definitions of habitability and prompt us to consider the possibilities for life in seemingly inhospitable locales, such as the subsurface oceans of Europa or the methane lakes of Titan. The ongoing search for extraterrestrial intelligence, SETI, adds another layer to our cosmic exploration. Utilizing advanced technology and methodologies, scientists scan the skies for signals or signs of intelligent life beyond our planet. The discovery of even the most basic form of extraterrestrial life would have profound implications for humanity, challenging our understanding of life's origins and our place in the cosmos. However, the quest for contact raises ethical questions about our responsibilities as we reach out to potential extraterrestrial civilizations. The potential consequences of such interactions, whether beneficial or harmful, underscore the need for careful consideration and dialogue within the scientific community and beyond. As we navigate the complexities of space, we also confront the profound implications of our own existence. The concept of the pale blue dot, famously articulated by Carl Sagan, serves as a reminder of the fragility and uniqueness of Earth in the vast expanse of the universe. This perspective urges us to reflect on our shared responsibility to protect our planet and foster a sense of stewardship for future generations. In addition to philosophical reflections, our exploration of space fosters a sense of unity among humanity. The cooperative efforts of international space agencies, private enterprises, and scientists from diverse backgrounds exemplify the collaborative spirit inherent in our pursuit of knowledge. The International Space Station, ISS, stands as a testament to this spirit, serving as a laboratory for scientific research and a symbol of global cooperation. As we peer into the cosmos, we are reminded that our understanding is always evolving. Each discovery unveils new layers of complexity, challenging our assumptions and inspiring further inquiry. The pursuit of knowledge is an iterative process. Each answer leads to new questions, propelling us further into the unknown. Looking to the future, the potential for human exploration beyond Earth beckons with promise and excitement. Missions to Mars, the establishment of lunar bases, and the prospect of interstellar travel are no longer confined to the realm of science fiction. These endeavors will require innovative technologies, interdisciplinary collaboration, and a commitment to sustainability as we extend our reach into the cosmos. As we continue to unravel the mysteries of space, we are reminded that our journey is a reflection of our innate curiosity and resilience. The universe is a vast and intricate tapestry, filled with wonders waiting to be discovered. Each step we take in exploration deepens our understanding of existence and reinforces our connection to the cosmos. In closing, the mysteries of space inspire us to embrace the unknown and seek answers to the questions that linger in our minds. As we gaze into the night sky, we are reminded of the beauty and complexity of the universe, a tapestry woven with threads of time, space, and possibility. Our exploration is a testament to the enduring spirit of inquiry, and the quest for understanding is a journey that will continue for generations to come. In this grand narrative, we stand united in our pursuit of knowledge and our desire to explore the cosmos. The mysteries of space beckon us to continue our journey, to seek answers, and to celebrate the wonders of existence. With each discovery, we deepen our appreciation for the universe and our place within it, reminding ourselves that the quest for understanding is a fundamental aspect of the human experience. As we embark on this journey together, we remain committed to unraveling the mysteries that lie ahead, knowing that the cosmos is filled with secrets waiting to be uncovered. Each step we take brings us closer to understanding the universe and, in turn, ourselves. As we further explore the mysteries of space, the concept of black holes emerges as one of the most enigmatic phenomena in the cosmos. These regions of spacetime, where gravity is so intense that nothing, not even light, can escape their grasp, challenge our understanding of physics and provoke deep philosophical questions about the nature of reality. The formation of black holes typically occurs when massive stars exhaust their nuclear fuel and collapse under their own gravity, creating a singularity surrounded by an event horizon. The study of black holes has evolved dramatically since their theoretical inception. In recent years, advances in observational technology, such as the Event Horizon Telescope, have allowed us to capture images of black holes and their surrounding accretion disks. The first ever image of the supermassive black hole at the center of the galaxy M87, released in 2019, marked a significant milestone in our understanding of these cosmic giants and provided tangible evidence for their existence. Despite these advancements, many questions remain. For instance, the precise nature of the singularity at the center of a black hole continues to perplex scientists. Current theories, including general relativity, predict that singularities possess infinite density and gravitational pull. However, this notion leads to contradictions with quantum mechanics, prompting researchers to explore potential frameworks that could reconcile these conflicting theories, such as quantum gravity or string theory. Additionally, the concept of Hawking radiation, proposed by physicist Stephen Hawking, introduces the idea that black holes are not entirely black but can emit radiation due to quantum effects near the event horizon. This phenomenon implies that black holes can gradually lose mass and potentially evaporate over astronomical timescales. The implications of this process challenge our understanding of thermodynamics, entropy, and information, leading to ongoing debates about the fate of information that falls into a black hole, a dilemma known as the black hole information paradox. Beyond black holes, we encounter the phenomenon of neutron stars, which are among the densest objects in the universe. Formed from the remnants of supernova explosions, neutron stars are primarily composed of neutrons packed closely together, resulting in extraordinary densities. A sugar cube-sized amount of neutron star material could weigh as much as a mountain on Earth. The study of neutron stars has revealed fascinating insights into the fundamental properties of matter and the behavior of extreme gravitational fields. One particularly intriguing aspect of neutron stars is the existence of pulsars, rapidly rotating neutron stars that emit beams of radiation. As these beams sweep across the Earth, they produce regular pulses, akin to a cosmic lighthouse. The precision of pulsar timing has led to the development of pulsar-based navigation systems and has provided insights into fundamental physics, including tests of general relativity and the nature of gravity. As we broaden our exploration, the search for life beyond Earth becomes increasingly compelling. The discovery of extremophiles on our planet has expanded our understanding of the potential for life in extreme environments. This has prompted astrobiologists to consider a broader range of conditions that could support life, including those found on icy moons like Europa and Enceladus, which harbor subsurface oceans beneath their frozen surfaces. The search for biosignatures, indicators of past or present life, extends to the study of exoplanets, planets that orbit stars outside our solar system. Advances in detection methods, such as the transit method and direct imaging, have led to the identification of thousands of exoplanets, some of which lie within the habitable zone of their stars. The characterization of these planets' atmospheres through spectroscopy may provide clues about the presence of water, organic molecules, and other potential indicators of life. The ongoing exploration of Mars represents another critical aspect of our quest for extraterrestrial life. Robotic missions have unveiled evidence of ancient riverbeds, polar ice caps, and seasonal methane emissions, suggesting that Mars may have once harbored conditions suitable for life. Future manned missions to the Red Planet hold the promise of direct exploration and the potential for groundbreaking discoveries. In addition to our search for life, the question of the universe's ultimate fate looms large. Theories about the future of the cosmos range from the Big Freeze, where the universe continues to expand and cool indefinitely, to the Big Crunch, where gravitational forces eventually reverse expansion and cause the universe to collapse. Alternatively, the Big Rip scenario proposes that the expansion of the universe accelerates to the point where all structures are torn apart. As we contemplate these possibilities, we must also consider the implications of our actions on Earth. The exploration of space is intertwined with our responsibility to safeguard our planet. Climate change, resource depletion, and environmental degradation are pressing challenges that require our attention and collective action. The lessons learned from exploring the cosmos can inform our approach to sustainability and the stewardship of our home planet. The advancements in space technology not only expand our knowledge of the universe but also inspire innovation in various fields on Earth. Technologies developed for space exploration, such as satellite communications, GPS, and advanced materials, have far-reaching applications that enhance our daily lives. The interconnectedness of our technological advancements and our understanding of the cosmos exemplifies the reciprocal relationship between exploration and innovation. As we conclude this journey through the mysteries of space, we recognize that our exploration is not merely about uncovering answers. It is a testament to the resilience and curiosity of the human spirit. Each discovery propels us into new realms of inquiry, inviting us to ponder the nature of existence and our place within the vast cosmos. In this grand narrative, the mysteries of space encourage us to embrace uncertainty, foster collaboration, and inspire future generations to look to the stars with wonder and curiosity. Our journey is a reflection of our innate desire to explore, to understand, and to connect with the universe around us. As we continue to unravel the secrets of the cosmos, we do so with a sense of purpose and unity. The mysteries of space beckon us to reach beyond our current understanding, reminding us that the pursuit of knowledge is an ongoing journey, one that is as limitless as the universe itself. With each passing day, new discoveries await us, each revealing a deeper understanding of the cosmic tapestry that surrounds us. The universe is a boundless expanse of wonders, and our quest to uncover its secrets will continue to inspire, challenge, and enrich our lives for generations to come. As we embark on this journey together, we remain committed to exploring the mysteries of space, seeking answers, and celebrating the wonders of existence. The cosmos invites us to dream, to question, and to embark on a voyage of discovery that transcends time and space. In this endeavor, we stand united as a species, driven by our shared curiosity and the enduring spirit of exploration. The mysteries of space await, ready to unfold before us, challenging us to continue our quest and expand the horizons of understanding. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.